All right, we can go ahead and get started. Hello, everybody, and welcome to the Data Architecture Virtual Chapter meeting for February. My name is Kenny Neal, and today we are thrilled to have Kim Tripp back to talk to us about why physical database design matters. We end by Nutanix. We're very grateful to have them as a sponsor. Please check out the URL at the bottom of the screen there and thank them for sponsoring us and helping make these webinars possible. Here are some of our upcoming meetings. Next month we've got Tim Radney on the 14th talking about SQL Server performance and getting started tuning. I hope you can join us all for that. And then the Data Architecture Virtual Chapter is just one of several virtual chapters that PASS has available. You can find anything, a bunch of different topics. Go ahead and give those a check. They usually meet around lunchtime or some of them in the evenings. Just a lot of great information. And without any further ado, I'm going to go ahead and switch it over to Kimberly. All right, Kimberly, you should have control now.
Okay, I just unmuted myself as well, so hopefully everyone can hear me. I'm going to assume this.
I can hear you.
Okay, I didn't hear anything. So. All right. I could do this presentation for one very quickly. All right, well, thank you very much for everyone that is here today for the PASS Virtual Chapter on Architecture. I remember giving a presentation with Kenny a while back, and he said this is a topic that people would really enjoy hearing about, and he knows that I'm passionate about it. And in fact, I actually did a Pluralsight course, and I just wanted to mention that because if you guys are interested, we can give you a Pluralsight code so you can get online and see the entire course, which is 4 hours or so on physical database design. So I just wanted to mention that because there's so much here. I could probably talk for 8 or 9 hours on this topic, but it's certainly one of my favorites, and our team is talking to you guys, it looks like, for your next couple of meetings as well. So I think you guys are probably pretty familiar with us. I have a couple of quick obligatory marketing slides, but I'll go through those quickly. The only thing that might be interesting for some of you is our Insider program. We just send 2 emails a month and tell you about all sorts of interesting things that either the team has been working on or classes coming up, things like that. So you guys can look through these slides, which, by the way, I don't know, Kenny, I don't know what your process is, but I will bundle up my demo and my slides so that you can post them on the website for the attendees to download after the fact as well. So, but if you're interested, we do have some in-person classes as well as our online training. And like I said, I've got a few slides here. IEPTO1 and PTO2 are probably my favorites because they're all around performance tuning. But we just don't spend a lot of time on architecture. I mean, we are talking a lot about architectures in our classes, but one of my topics that I wish I could spend days and days on is partitioning and data structures. And that's something I will touch on a little bit here because I think people just don't give it the attention it needs. If you're interested in a conference, we've got a conference called SQL Intersection coming up in May. Just another event that some of you guys might enjoy. And Pluralsight. This is probably the most important one for some of you guys that might want to watch the 4-hour version, or if you've got colleagues that don't think that database design matters, which I'm guessing for quite a few of you is the case. You can have them get a code. Just put something like PASS VC Architecture Pluralsight code in the subject line and send it to Paul, and he'll give you a code so that you get 30 days of access to all of our SQL Skills content, which is totally free, no credit card, no catches, nothing like that. So anyway, my name's Kimberly Tripp. I've been working with SQL Server forever. I'll let you guys read all this background stuff, and I just want to get to the technical content. That's my favorite. I hate the marketing stuff. But this topic specifically is one of my favorites because I find people will say things like, disk space is cheap, who cares? Or, you know, let's just get it out there and we'll deal with performance later. And I absolutely hate these kinds of responses because what they end up doing is getting a database out there that does not scale, and ends up being out there a lot longer than anybody ever anticipated, right? I mean, sometimes people are saying, oh, we just want to see if people are interested. We just want to see if it works. We just want to see this, that, or the other. And the next thing we know, 6 months, 9 months, a year later, that application that we thought was only going to be a few weeks, out in the world is still out there, and it's hobbling along, and now it's becoming a critical application, and we can't fix all of the problems because schema changes can be really difficult to make in a production environment. In fact, I would strongly recommend against making schema changes most of the time in a production environment. So what does that mean? It means that we have to suffer with poor performance. We have to, put Band-Aid fixes in as much as we can to try to make things limp along faster. Sometimes we might be able to hobble better performance with indexes, maybe more covering indexes, but then that requires more disk space, and it can start to negatively impact OLTP performance. So there's a lot of problems that go along with bad design. So I have a couple of slides just to kind of give you some insight into why physical database design matters, a few things to think about, and then the examples that I'm going to focus on are mostly around data types and table size and wasted space, and then data types and index size and wasted space. I am getting some questions in the question window, and I am going to try to look at this throughout the presentation. Someone said, please share the Pluralsight code. We have to do that on an individual basis, so you have to send email to Paul for the Pluralsight code. And as far as the SQL Server Internals book, that's Kaylin Delaney's, and I'm sure she's planning on a VNext version of the book, but I don't know the current status of that. But you're right, I did write the indexing chapter in one of the past releases on that one. So, but anyway, let me get into this topic. Does physical database design matter? Well, obviously I think it does, otherwise I wouldn't have a whole webcast around this. But the point of kind of why does this matter, those two phrases that I mentioned, let's just get it done, we'll deal with performance later, or disk space is cheap. I hear this one all the time. Oh, who cares about 4 bytes, 8 bytes, 16 bytes? And I get that, because when you're looking at one column and you're trying to decide on a data type, sometimes that column maybe doesn't make much of a difference if it's 4 bytes or 8 bytes. But the point is that you guys don't have just one row. And you do need to think about the cost of your design at scale. You have to think about the cost of your design with thousands of rows. And come on, thousands of rows? If I were to ask, and I don't know if I can get a quick show of hands or some way to do that. I suppose I can with a poll, but if I ask you guys, I don't even need to ask you this, to be honest, but if I asked you how many of you guys have tables with at least 1 million rows, I would bet money on the fact that pretty much everyone out there has at least 1 or 2 tables with 1 million rows, and some of you are probably laughing at me right now saying, only 1 million rows? I've got a table with hundreds of millions of rows or billions of rows. And when your tables start to get large, the design of those tables is incredible. It's critical to the overall scalability of that table. And in some cases, you're going to be surprised at how much bad design can actually really cost you. So that's what I'm going to focus a lot on here. And people think that, I'm trying to tell you that you should spend 6 months in design. That's not what I'm saying either. I mean, design is relative to the importance and criticality of the app and the overall size of the app. But what I do want, so telling you 6 months is arbitrary anyway, but what I do want you to think about is how is that schema going to scale? And how are my features? This is probably one of the most important things, not just performance related, but even usability related, but how are my features going to work together? I find that a lot of people think about their tables and then just start piling on the features that they want to use, thinking that there's never going to be an issue with those features together. And I've actually had exactly that, where I was consulting with a client and started to think about some interesting features that they wanted to use, and I said to myself, wow, I've never combined full text indexing, partitioning, and this, that, and the other. And I thought, I should try this out on a smaller version just to make sure that I can do everything that I wanted to do. And that was when I learned that full text indexing doesn't support fast switching, or I should say partitioning doesn't support fast switching when there's full text indexes on the table. And here was a customer that wanted to go with this, pretty elaborate schema, and two of the features that I knew they wanted to use, I found out wouldn't work together. I mean, this is years ago now, but my point is doing a little bit of prototyping, do a little bit of work with that schema and the features you think are going to, be used together, and you might end up heading off some problem really early. And I could give you so many good examples of this, even with existing applications. Applications that are out there, and I won't name names, but applications that are out there that didn't look at things like maintenance, and they had a whole bunch of log columns in the production tables, and then they couldn't take advantage of online index rebuilds, because it wasn't until SQL Server 2012 where you could do an online index build if the table had log columns. So there are so many features that people don't think about, and don't think about things like maintenance. And now customers who've bought that product, that bought Enterprise Edition wanting to take advantage of enterprise features, can't because the schema doesn't support it. So understanding the physical, and what I mean by the physical implications are the implications caused by the model itself in that physical environment, right? You guys might have a model, but you might put that model into Oracle. You might put that, no, none of you would do that, right? You put that model into SQL Server, and the point is, when that model is in SQL Server, what does SQL Server impose potentially as limitations or requirements on that schema? That's what I mean by physical database design. And in my opinion, no matter what environment you're going to put that model into, you need to understand that back-end system. You need to look at what implications that schema is going to have, because it could be a feature problem, it could be a performance problem, and so let me start getting into that. As far as why it's important, I think that's pretty obvious, right? What I see a lot, though, and I know some of you can bond with me on this one, is that when database schemas are developed in development environments, they're often not tested with production volumes of data. And I get that. That can be challenging, especially a new application where you don't even know necessarily what the production volume of data is going to be or is going to look like, which is very challenging, right? You might not have a lot of users to be able to do testing with, right? So there are a lot of things that development doesn't see and doesn't necessarily test for. To be honest, I would really strongly recommend, depending on the number of users and the criticality of the application, that more time be spent in prototyping and QA to make sure that the application will scale by simulating production volumes of data and production workloads. But again, none of that is ever perfect. I mean, if I'm being really honest, no matter how much we work and look at QA and test, it's never exactly what production is going to look like. And the reason why is users lie, right? And no, I don't mean users lie per se, but users are very myopic, right? Users only know what they know. Users only tell you what they think is important. So you as a developer or an architect are going to focus on those things that they said were important, where once that application actually gets into production, what is critical and what becomes the most frequently accessed data or frequently requested data might not be what you thought it was going to be. So even though you may have done tuning and you may have done what you thought was appropriate, what actually happens in production might actually be a little bit different than what you anticipated. So I always talk about tuning as taking multiple things. But let's go back to design. The more that you look at the impact the environment's going to have on that design, and the earlier you do so, the more you can probably take advantage of that physical environment. And I kind of make the point at the bottom here, you know, can you imagine using a chainsaw without reading the manual? I mean, maybe that's a bad example, and personally, I probably should never use a chainsaw, even if I do read the manual. But my point is, you really do need to, you know, read the manual, figure out how to use the tool correctly so that you don't get hurt, so that you actually are successful. So, continuing on with this concept, what does it actually mean? Well, I already mentioned a little bit about this, right? There's the logical side, you know, what is the data, what are we going to store, how are we going to break that down into our different attributes and tables, right? But then there's the question of what happens when we push those structures into our physical environment. And a lot of people think that physical design is just, you know, oh, I need to know T-SQL, or I need to know PL-SQL, right? I need to know the language for that RDBMS. But for me, it's a lot more about what is that physical architecture going to do, or that physical environment going to do to my architecture. And this is, I think, most obvious at the very bottom of the slide. If you want something that's truly scalable, you do need to know the data, right? And what I mean by that is the criticality of the data, the churn. And what I mean by the churn is the volatility of the data. Is it going to change a lot? Are we querying it, right? Is this particular table going to be queried more and relatively stable at some point in time? Or is this table, you know, volatile? Every minute of every day, we're inserting thousands of rows into it. So when I say know your data, I really mean know your structures, know the domain of legal values for your columns. But as I started to talk about your data, you can't know just the data. You have to know the workload of your data. You have to know the churn, the criticality of the data. You need to know the stability of the data, the volatility of the data. But that's where a lot of people stop. They look at their schema, they get some insight into the application, and they think, okay, I know enough to create, to design, and ship it. And they don't really think they need to know the platform. They don't think that knowing how SQL Server works is critical to performance or scalability. And this is where I feel that, you know, most of us as SQL consultants or instructors come in. We kind of put in that missing piece and explain why something worked the way that it does, or how changing your design could offer you more options, more features, more capabilities, or could offer you the ability to, let's say, take advantage of online indexing. Like a great example, you know, for some applications that are out there that have a lot of log columns in the table, if they didn't upgrade to 2012 or higher, you know, really, at the time they developed those applications for 2005 or 2008, if they had just vertically partitioned their tables and separated the core critical columns from the log columns, they could have, for their core critical data, continued to do online operations and had the log columns in another table. So there were options that they could have used at the time they designed those tables, but they didn't. And now, if that application was designed for 2008 or 2012, it might take many versions before they could fix it, or it would require the customers to upgrade, right, to take advantage of the new features. So it's very frustrating. There are often other strategies that people can use, they just don't look. As far as prototyping, I have a different slide in the Pluralsight course on this one, because I actually just had a consulting engagement where a client proactively, I was so impressed by this, a client proactively asked me, what should I do in my tables to think about, you know, now, if those tables might end up becoming large and need to be partitioned in the future. They didn't think that they would need partitioning for 6 or 8 months. They didn't necessarily want to start with partitioning. And what was interesting is they came to me first and said, what can I think about? And what I've seen as a very common scenario is after the fact, people have very large tables and they hear that online indexing can be used to partition a table while users are using it, which is actually very cool. And that is true, right? You can take a table, rebuild its clustered index on a partition scheme with an online clause, right? Doing that as an online operation. And if everything is set up correctly, you can actually rebuild and partition a table as an online operation. And that actually might work with very few problems. In fact, that often does work. However, and you might not know this, but when you build the clustered index on a partition scheme, the base table essentially is partitioned, but the non-clustered indexes don't go along with that, and they stay what we call unaligned to the base table. So you don't have fast switching in that partition table until all of your non-clustered indexes are aligned. However, you might not be able to align those non-clustered indexes because there's a requirement that any non-clustered index that is unique also has the partitioning column as a member of that index key. It doesn't have to be the leading column, that's another common misconception, but it does have to be in the index. So this is a very advanced, geeky scenario, but my point is people that want to consider partitioning often jump into it without really understanding all of the implications. And as a result, they can end up having problems. They might end up putting themselves into a scenario where they're going to require downtime, they're going to have to change their schema, they're going to have to fix their application code, and of course that's going to be costly in terms of availability because of the downtime. Of course, what about all the testing that has to go into changing the schema, changing the application for the new schema, right? So there's a lot of potential problems if you don't do any prototyping or any testing of your schema before that application is in production. Because once it's in production, it becomes much harder to change. Now, a couple of very interesting questions that came up on this. Does partitioning help with performance issues, or is it more of a storage optimization? It's actually designed mostly for manageability, but if done well and if done correctly, there are some performance benefits that you can get. A lot of the performance benefits are around things like large-scale batch operations, but they can even be with regular queries themselves. But that's a huge can of worms for a whole nother few days, basically. That's a tough one to get very quickly. And I do have another comment that Daryl put in here that says, don't you think part of today's problem is that many practitioners didn't, quote unquote, grow up like us old timers, right, Daryl? Where resources were scarce. And I totally agree with that. I look at my laptop and I laugh and I think of the power in my laptop right here. I've got a laptop now. Before I brag about how great my laptop is, beware that it's 9 pounds, okay? I have a massive behemoth of a laptop, which is a pain in the tush to carry around with me, but when I'm using it, it's fantastic, right? And thank goodness for wheelie bags. But I have a 8-core, 32 gig, I've got 3¼ terabytes of solid state drives spinning around in my laptop. And the reason why that's interesting is I can get away with a lot of crappy code before I even realize the impact of that crappy code. And this is what you guys are dealing with too. Development often doesn't see the implications of their crappy code because they get away with so much on their machines that don't have realistic data, don't have realistic workloads. So that's why so many of these things have to be better evaluated earlier. We're not seeing the proverbial stuff hit the fan until production because we haven't really done enough work during design and during QA and test. So it's a big problem, and I see a few of you commenting that there's a lot of problems with quote-unquote bridging the gap is the term that I usually say. You know, the gap between database developers and database development. Database development and the storage admin, or the Windows admin, or the SAN admins. There's a lot of people that have to work together earlier. It's so interesting. I did a presentation years ago that actually was called Bridging the Gap Between Database Development and Database Administration. And what was interesting, you know, some of the things I focused on is that, you know, database developers, just to give this example, database developers and database admins often don't get along. And yet, if they did communicate earlier, database developers could learn a lot from what the DBAs have learned, but DBAs could learn a lot about the schema that's coming down the pike if they talk to the developers earlier. And if you just get those two groups together, there's so much headache and nightmare and performance problems that you could really, you know, head off before they happen that would make everybody's lives a lot easier. So I'm a big fan of having stakeholders from the different organizations discuss applications while they're being conceived, right? And while people are looking at and talking about the requirements. And I think you would go a long way to fixing a lot of problems before they happen, which is an interesting discussion too, because some people say, well, if you fix a problem before you happen, how do you know if something's worth? And that's a really interesting tangent that I'm not going to cover here, but it is an interesting one. Now, does data, let's get into the two that I want to focus on, right? Does data type choice matter? Well, obviously, I think it does. These are the two topics that I'm going to focus on, data types and table sizes, and data types and index sizes. You know, an integer is 4 bytes, a big is 8 bytes. You know, if we think the application is going to be out there for a while, why not just make everything an 8-byte integer? And I get that, and I'm fine with that if you think that that table is going to be large. But what I don't want you to do is, quote unquote, have a standard where everything that's a number needs to be a big int. And you might think, oh, who would do that? I can't even tell you how many times I've gone into an application environment and I've looked at like a date. A date is a great example, especially because so many applications have grown up using date time. And I remember this application where everything was date time. And if you start to look at things like birth date, and let's even be more specific, birth date of an employee for a company that, you know, has only been around for 30 years, right? So what would be a valid birth date of somebody that works for this company, or even somebody that doesn't work for the company anymore? Like, I'm not worried about January 1, 1900, you know, and I could get away with using a small date time rather than a date time data type. But yet I've gone into databases where, like, everything is date time. They didn't even look at small date time, or everything is date time 2 now, the new data type, which is way more precise. I would use date time 2, but if you haven't looked into date time 2, you can actually describe date time 2 with a parenthesis. If you look at that third bullet right here, I don't know if I should draw, but right here, you can actually describe your date time data type, date time 2 data type, with a parenthesis of any number 0 through 7, and that tells you the precision of that date time 2 data type. That's hard to say. Now, date time 2 7 gives you 7 digits of precision, which is incredibly precise for most of you. You probably don't need that level of precision all the time. But if you do, date time 2 7 is 8 bytes. What's interesting is that date time 2 3, for example, with 3 digits of precision, is actually more precise than the old date time 2 data type, or the old date time data type, but it actually takes less storage. And you can see that in the books online. It'll actually tell you that date time 2 ranges from 6 to 8 bytes in storage, depending on the level of precision that you ask. So you could go with something that's pretty precise, but yet still take less storage. But you could also consider doing something like small date time when you are storing a date without much of a time. But then you could also go with a numeric, a formatted numeric even. I mean, there's all sorts of options that would take less storage, And if it's one column, is that big of a deal? Not necessarily. But if it's 10 columns across multiple tables and foreign keys, it really does start to change in terms of scale. So let me explain what I mean by that. If you just took 2 columns, let's say, that you defined as date time and really could have gone with small date time, and this is, I've gone to tables where I've taken 6 or 8 or 10 columns, so I'm actually, I'm on the small side here of saying just saving 8 bytes, right? And a lot of people would say to me, you've got to be kidding me, 8 bytes is not going to make a difference. I want you to think about those tables that have millions of rows. And somebody did actually comment that they were laughing when I said, oh, just millions of rows. For some of you that have billions of rows, this is a crazy amount of space. In fact, have you ever actually thought about it at scale? Look at this. If you save 8 bytes over 10 million rows, you're going to save 76 meg. Okay, who cares? But at 1 billion rows, you're saving 7.6 gig. Can you believe it? I mean, it's kind of crazy, but for some of you that have billions of rows, you are looking at gigabytes of savings just by having tweaked your schema a tiny, tiny bit. Now, for some of you, you might be tweaking your tables a tremendous amount because you have 8 or 10 columns that were inefficiently designed. So you're saving just 32 bytes, but at, let's say, 100 million rows, you're already saving 3 gig. And again, I look at some of these numbers and I think to myself, okay, the problem though is not just one table. And that's all I'm showing here. It's like one table with 100 million rows. For some of you, you might have dozens of tables, dozens of databases, right? So it's impossible to design well if you don't think about things like data types. I even saw an email on an alias that I'm on of very knowledgeable SQL Server people, and somebody said, does anybody even think about disk space anymore? Because everybody's just using solid state. And I just kind of thought, are you kidding me? I mean, solid state does help with some performance problems. That's true. But it doesn't solve all performance problems, okay? And in fact, it might help with random IOs, but it doesn't help with inefficiencies of a page, right? Because you still have to read that page into memory. And if that page is wasting 20% of its space, that means you're reading probably 20% more pages. And great point, that's not just disk space. A couple of you have already said this, right? It's not just storage. I totally agree with you, Armando and Daniel, right? And Daryl too. It's memory. It's backups. A presentation that I did for PASS, I think it was 2012, was about GUIDs. And it's interesting. When people go crazy with GUIDs, something they don't think about is even when you compress a backup, GUIDs are less compressible. And I created a scenario in that presentation where I ended up having, integers used versus GUIDs used for a variety of tables. And it was amazing, not just how much bigger the database was, and not much how much more memory and how much more disk space and how much more IOs and how much more logging it had to do. But when I went to do compressed backup, right, the backup compression was horrible in the GUID-heavy, GUID-centric database. I wish I had the numbers right here, but it was something like 90% for the integer-based database and 50% for the GUID-based database. And so it's one of those things where people don't look at the entire scale of what they're doing, right? I've got some great comments here. Another great one from Peter, right? You're putting this on your network as well. So you're transferring more data over the network. You're requiring more data on disk, more data in memory, more data in the backup. Okay, this is great. You guys are making some fantastic comments, but we're all on the same page here. When you think about the scale, it really does add up. It adds up to all of these things becoming problems. It's like death by 1,000 cuts, right? There isn't one little thing you can do anymore to get much better performance. You can add some indexes, but even your indexes are bloated, right? Your indexes have more junk in them, more wasted space than they need to. So now, you know, you might get some better performance, but you're not even getting the best performance with the index that you could have if you had smaller data types. So let me kind of focus on this concept of indexing in a second. I want to round it out. I do want you guys to use common sense when it comes to data types. I really don't want you to, you know, you have 187 customers, so you've decided that your customer ID is going to be a tiny int. I mean, come on. I hopefully you guys are laughing at that one. You know, you do want to think, okay, let's at least go small int. To be honest, I might even be more optimistic than that and go with an integer, right? Hoping that I do get into the hundreds of millions, if not billions of customers. But for a lot of us, a small int might be fine, right? But an integer, I would say, would probably be a better choice. Do you really need to go with big int? That's debatable. But for your sales table, I really would probably consider something like a big int over an int if you think you're even going to go into millions or tens of millions of rows. Because for any of you that have ever had to fix a data type that ran out in production right now because you could not get any more data into that table, you'll know that it can be a real pain in the tush. So I would use a little bit of forethought. I would think, you know, how long do I want this application to last? And then realize that you're probably way underestimating it, and think much further out than that, and opt on something like a big int over an int. So common sense is very important here. Don't standardize, though. Everything's an int. Everything's a big int. Everything's a date time. Everything's a date time. And I've seen that where, you know, you need to use a date, use date time too. And like that's it. That's what their, you know, design guide says. And in fact, that's not a bad idea. I don't see these done as much as they should be, but you guys should have some type of standards doc that your team uses. And you might think, oh, right, like we're ever going to do a standards doc. I know that people don't think about this stuff up front, but what I really want you to do is work with your development team, have the DBAs get together and talk about the top 20 or 30 things that you've seen as problems. Start to build a document from that, right? And then just have people regularly review it, add to it. Make it part of your regular standard operations. Have your teams get together regularly to talk about these things. And I know this is huge. I know I'm throwing things out there that are difficult for you guys to do, you know, culturally, politically, on some of your teams. But it is the thing that you're going to have to do in order to get performance to be more scalable longer term. It's the thing you're going to have to work toward. You're going to have to show an example in the past where, you know, show something that could have been prevented, something that maybe has already happened to you guys and you saw as a big problem. Show that problem and show how, maybe to management, how that could have been prevented if you had worked with development, and show where the power of development and DBAs and network ops and where getting together can actually help everybody. And then maybe they'll put some more effort into it. But I totally agree with you. It is huge and very difficult and very challenging to tackle in some of the environments that you guys are in. I'm totally with you. But it is something that does really help in the long run. So if you can put the effort into it, it'll pay off. So the thing I want to talk about more than anything, because I think this is one of the biggest design decisions that is undervalued and mishandled most of the time, right? And that's the data types and your indexes. And I kind of mentioned, of course, that your data type impacts table size, but what about indexes? Like, does it cost me anything? Does it cause me any grief? And of course, if it's just a wide data type, then it's going to make your indexes unnecessarily wide. That's true. But the one that impacts you the most is your clustered index choice. Because that clustering key, and this is the part that people don't really look into that much, but the clustering key, whatever is the column definition for the clustered index, that key is used in the non-clustered indexes to help look up data when we're using a non-clustered index to access data in a query. And I'm going to give you some more insight into this in a second. Now, I did want to mention column store here, even though I'm really not going to discuss column store. They have a different structure. The different options that you can look at for column store actually varies based on the version that you're on. The only reason for even putting column store in here was really for me to throw in a little tangent here on upgrading, because so many people are still on 2000 and 2005 and even on 2008. If you're debating on what version to go to, I have to tell you, there is nowhere to look other than 2016. You can back up restore from 2008, not even R2, 2008 to 2016. There is absolutely no reason for any of you to consider 2012 or 2014 unless you've already done all the testing and you're just about to go there right now. I would even argue that you might want to consider doing the testing on 2016, push it out a little bit further, and then just go straight to 2016. There's two huge features in 2016 that I'm the most happy about. One is column store and all of the restrictions that they've reduced and eliminated from 2012 and 2014 with column store. But there's also things like query store. So if you haven't started to look at 2016, look into those features and consider going to 2016 as opposed to any other migrations if you're still on like 2008 or 2008 R2. Now, of course, all of this is predicated on whether or not your application will work on 2016, which if it's your application, you can test. If it's a third-party vendor, of course, you have to make sure that they support it and so forth. But my point is, if you have a choice, my choice is generally to go to 2016 instead of any other. So let me discuss the indexes, and I do see a few questions that have come up. I'm going to hit a couple of those in here, and then I will stay for questions at the end for the things that I don't get to, because there are a few things that I know I'm about to talk about. So let me explain a little bit about how non-clustered indexes work for those of you that don't know index internals. Indexes are one of my favorite topics. I love to talk at length about the internals, the structures, and the implication. We just don't have that much time here, and my goal here was to explain the impact of your design decisions without necessarily going into all the internals, but giving you enough to really understand why. And the book analogy actually will do that for us. If you think of a book with indexes in the back of a book, I mean, this is pretty straightforward. At some point, I know that I'm going to have people out there that are like, a book? What's a book? Book is internet? No, I mean, I'm kidding, but you know, it's funny because a physical book, I don't know how many of you are still messing around with physical books these days, but if you think of a book with an index in the back of a book, right, that index is alphabetized, and that gets you to the data within the book by using a page pointer. I mean, it's really simple, right? And if you think of books on animals, that's probably the best example for me to use because it's one of the few books that I've ever seen that ends up having multiple indexes. There's almost always an index by the species common name, but then there's almost always an index by the species scientific name, right? So there's two indexes in the back of the book. And if you think really hard about that, right, what is that index? Like, what does it consist of? And it consists of duplicate data, right? The species common name, the species scientific name is obviously in the book, but we've duplicated that information in the back of the book, and then we've sorted it with some type of reference into the data. That's what non-clustered indexes are. I mean, they really are just like this. I mean, very specifically, the leaf level of a non-clustered index is almost exactly like an index in the back of a book. But the pointer is different, okay? The pointer is actually the clustering key, and I've got a slide to talk to this. The idea, though, is that the book has one form of ordering, like your table, right? But to actually find some of the data, you go to the index, and it helps you reference it, right? Again, by using a page pointer. You go to the common name, you look up that value in that very easy sorted structure, and then it says, oh, go to this particular page. Once you find that, you do what a lot of us have referred to as a bookmark lookup. In fact, in SQL Server, there used to be a time, it was actually 2005, where the show plan used to actually say bookmark lookup. Oh, actually, was that 2000? Yeah, in 2005, they ended up changing. Wow, God, 17 years ago. But the show plan used to actually say bookmark lookup. It doesn't say that anymore, but that's what's happening when you go from a non-clustered index into a clustered. So let me be more specific, okay? You know, that lookup depends on how the book has been ordered. If you think of a non-clustered index specifically, there's a structure to a non-clustered index, and there's basically the leaf level structure, or let's just say one part of a non-clustered index, because you don't have to geek out on the actual names of the structures, but there's basically a structure that's called the leaf level that looks just like the index in the back of the book, but we, as humans, have to use that structure and go through it knowing where a letter is alphabetically, right? So how does SQL Server go into that structure? It puts a navigation structure over that leaf level, and that's called a B tree, okay? So that non-clustered index B tree doesn't exist in a book, but it's what SQL Server uses to get to the leaf level efficiently. We're not going to worry so much about the B tree structure here. We're just going to talk mostly about the leaf level structure. So now that leaf level structure, just like the structure in the back of a book, has to have a pointer. Now they could use a page pointer. They could use kind of a row ID or a RID, as it's often been referred to as, but they don't. They used to. For some of you thinking, that's really stupid, they should use a RID, well, I suppose you could probably find SQL Server 6.5 somewhere on eBay if you really want to use that. But let me tell you, the performance of using the old RID-based structures and what we call a volatile RID was not very efficient. They actually changed in 7.0 when they changed the physical structures to using the clustering key as the lookup value. And while this did solve a lot of problems, it actually created some as well. It creates the biggest problems for people that don't understand the physical implication of doing this, right? And this is why this is such an important discussion, right? If you just let the defaults happen, if you go into a table and you design your schema and you put a primary key on the table, and maybe your primary key is a natural key. I don't know if some of you have heard this term, but this is probably one of the worst primary key clustered indexes that could possibly exist. Notice I'm not even saying Google's yet, okay? But the worst clustered primary key is a primary key that's clustered on a natural key. So what do I mean by that? Right? A natural key is where maybe it takes 6 or 7 columns to naturally, uniquely identify a row. So imagine you don't have a part number, but your products consist of like a manufacturer and a type and a subtype and a size and a shape and a whatever, right? But you've got 6 or 8 attributes that uniquely identifies that row. That's often called a natural key. So then you go with SQL Server and you say, this natural key, I want this to be the primary key. So SQL Server says, okay. And behind the scenes, that primary key is then used as the lookup value for that row. So for each non-clustered index that you tack onto that table, all 6 or 8 of those columns have to be duplicated into those non-clustered indexes in order to look up the row. This can cause you huge, huge costs in disk space, in memory, in backups, I mean, in all those things we've been talking about. So let me be more specific. And I'll show you a scenario here. Imagine that I have a table that is employee information. I thought this was a really easy visual for most of you. So, you know, we almost always have a table that is like employees, customers, things like that. And it's very important to understand, because I am having somebody that said, I thought the non-clustered index used the RID as a hidden column in the non-clustered index. not if the table is clustered. This is a great question, right? I mean, it's a great point, right? If the table is clustered, then the clustering key is used for the lookup. And so our decision on choosing that clustering key can have a huge impact on the efficiency of our non-clustered indexes. So I'll use this example. So I have an employee table, a customer table, and imagine for employees we have a non-clustered index on Social Security number. So this is going to be one of the indexes that we add to the table, but we're not going to cluster our table by Social Security number. We're going to choose something else. And imagine that our first choice we're going to talk about is clustering the table by last names. And I could probably explain a good reason to do this, right? I could probably kind of convince you that this is a good thing. Like imagine that most of your queries are by last name groups, like span of control is a common concept here. Like I want to find all the employees whose last name is Esther Z. If you think about it, right, all those rows, if my data is physically ordered by last name, would all be right there. I mean, doesn't that sound great? A lot of people would say, yeah, that sounds great. But what a lot of people are not realizing is that that's not how that table is going to stay. That table, as we insert new rows, is going to have to make room for those new rows. And something called splitting is going to occur. But that's still not even the biggest problem. I'm not even complaining about fragmentation here. There's bigger problems than this. And some of those are around the non-clustered. So imagine the non-clustered had the lookup value of just Smith. Well, which Smith, right? Which Smith? Well, the first Smith that goes in is just Smith, yes. But the next Smith that goes in has to be uniqueified. And if you don't know much about a uniqueifier, that's probably good. I actually kind of hope that you don't. But it's a 4-byte integer that has to go to uniqueify that row. So then there's Smith 1. And then Jones goes in, and Jones is just Jones. But then the next Jones goes in, and it's Jones 1. And so the uniqueifier uniqueifies the rows by the duplicate key. So the next Smith is Smith 2, the next Jones is Jones 2, the next row is, let's say, Anderson, that's just Anderson, but the next row is Anderson 1. An interesting and very geeky technical and kind of internals tangent on that is, what is the next uniqueifier value for a duplicate value? You have to look, right? You have to scan the last page of values for that, you know, Smith, Jones, to see what the max is to increment it by 1. I had a customer that was clustering by day. And so all of the rows for like February 9th, 2017 go in as February 9th, 2017. So as you insert into that page, we have to scan the page to figure out max, 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 new page. And then it's a little bit cheaper initially, but then as the page starts to fill, looking up the max becomes slower and slower. So my point, this is a very bad idea. I do not want a clustered index that has to be uniqueified. I absolutely want a clustered index on something that's unique, which is part of why clustering on the primary key is a good thing, right? Because the primary key is going to require uniqueness. So that's one aspect of clustering the primary key, which is good. But not all primary keys make good clustering keys, okay? So there's multiple problems here too. I didn't even get to the width of the last name, but how big is the last name? And is it an n-varchar, not just a varchar, right? So we have uniqueness problems. We have volatility. I didn't even mention that, but imagine having 5 non-clustered indexes and somebody's last name has to change. Well, then we have to update it not just in the table, but in the 5 copies that have been made for that last name in those 5 non-clustered indexes. So this is a horrible clustering key. And to be honest, this idea down here falls apart anyway because of fragmentation, right? Now, what if I clustered on a GUID? Because some of you might say, well, that solves my uniqueness problem. Oh, okay, I'm with you on that one. It does solve my uniqueness problem. But for a lot of you, a GUID is not needed, right? Needed. You might choose to use one for the simplicity of it, but you are probably wasting space and choosing something that is kind of overkill for what you're doing. Some development environments don't want to reconcile with a central server authority to get a unique ID. They don't want to have to talk to the server to find out the next ID, like if you have parent and child rows that you're creating at the application level. They think, oh, I'll just generate a GUID, that's my parent, I'll generate my child rows using GUIDs, I'll throw all of that at the server without making any other round trips, and I know it's going to work because my GUIDs are unique. So they use GUIDs because they think it's incredibly simple in the programming of it. And while it does simplify the programming aspect of it, it causes other problems. And I would even argue that talking to the server in the batch and programmatically inserting a row, finding out its key, and then inserting that key for the child rows is not difficult programming, okay? It's just, some people just don't even put the effort into it. So it's really, really interesting when you talk through, like, why are we using a GUID? And sometimes it's just not necessary. But some of the problems that it creates here is that the lookup ID is wider than it would need to be because a GUID is 16 bytes. And I did have somebody once say that they couldn't use an int because they were going to run out, so they needed to use a GUID. And there is big int, okay? And a big int is only 8 bytes, and you're not going to run out of big int anytime soon. Big int is a very large number. In fact, I think Paul did the math once and said that if you inserted 100,000 rows a second into a big int, it would take 2.95 million years before you'd run out. So you're not going to run out of a big int. An int, yes, an int only goes to 2 billion, okay? For many of you, you don't want to use an int. But a big int is fine, and a big int's only 8 bytes, whereas a GUID is 16. So I would argue that even though it's unique, it's unnecessarily wide, it's probably not volatile, so that's good. So it's static. And I guess the biggest thing is that you're now putting 16 bytes into every non-clustered index. So if you have 6 or 8 or a dozen non-clustered indexes and a table that's a billion rows, you'd actually be wasting tens of gigabytes just in having chosen a GUID versus a big int, which is crazy, okay? Now, there are some other reasons to use GUIDs, and I'm not saying never use GUIDs. I'm just saying to really evaluate whether or not a GUID is necessary, because I think there's a lot of cases where they're chosen when they don't need to be. And then the last scenario is something like an integer. Imagine that I use an integer. I mean, if employee ID is currently, 87,000, something like that, am I really going to get to billions of employees? Probably not, right? So the point there is I could probably very confidently choose an integer for employee ID, but for things like customer, I might want to use big int, right? So you do want to be and use common sense and be logical about, the long-term, use of that database. But in a lot of cases, just bumping up a little bit is more than enough. Like employee ID and integer is probably fine. And now I have a key that's only 4 bytes instead of 16. So I'm taking up only a quarter of the space in each of those indexes, right? So that's a much smaller structure that I would have. Now, I'm not getting into fragmentation here. That's not really my primary goal, but there are some secondary benefits, but there are also negatives. Fragmentation is a whole other discussion for another day. There are some good resources out there for you. I know Paul's got a course on Pluralsight, so if some of you guys go to Pluralsight, you can look at Paul's course on fragmentation. But just talking about the lookup values, the big difference here is the size, the volatility, the uniqueness, and the cost of the lookup value. And let me talk about this at scale, right? Every table in this little case might have 80,000 rows, and if we start to do the math, how big is the table, and then how much does each index take up? Well, let's talk about that. I'm actually going to do a demo for you, and I'll round out the lecture today with the demo. I've only got a couple more slides, and then I want to show you this. So this clustering key, like I said, does have an impact to your non-clustered indexes. A great point that was brought up is they do only add the clustering key columns that aren't already present in a non-clustered index. That's a great point. Like if you have a clustered index, here I'll switch over for a second here and just do, if your clustered index is on column 4, column 6, and column 7, which a multi-column or composite clustered index in and of itself is not a problem, especially if those columns are very narrow, if the combination is unique. I mean, I do want your clustered index to be as small as possible, but it doesn't have to be just a single column. There are many cases. In fact, the demo I'm going to show you is a composite clustering key. But if you do have a clustered index on columns 4, 6, and 7, and then you go and create, let's say, non-clustered index 1, whose key is column, let's say, 2, and then column 6, what's really interesting is the leaf level of non-clustered index 1 is C2 and then C6, and then any of the clustering key columns that don't already exist. So C4, then C7. Now, it's a little bit more challenging than this because I didn't tell you whether or not non-clustered index 1 was unique or not, but depending on whether or not it's unique or not, the B tree is going to be different. And this is where the index internals come into play. So if non-clustered index 1 is not unique, so you just create it as a regular index, then what's interesting is all 4 of those columns have to go up into the B tree for navigational purposes. And I have a blog post that talks about clustering key up the tree. And what I'm doing by putting this little note here is I'll put a link into the resources to that blog post so that you guys can read that. Now, just to round out this discussion, because I do want to get to my other demo as well, but if non-clustered 1 is unique, then the B tree actually only has the non-clustered key columns go up the tree. So anyway, I will point you to a blog post to explain more on that, but this is something that's interesting because unfortunately, if you guys use SP Help, right, like SP Help Index only shows you the explicitly defined columns in the key. And that's interesting. In fact, somebody even asked a question on Twitter today, and the blog post I'm going to write this afternoon, I promise I'm going to do this, is going to talk a little bit about why and when I would put the clustering key columns in my non-clustered index definition. So I will explain more on that later today in a blog post, so stay tuned on that one. But SP Help Index doesn't show you the stuff that SQL pushes into the tree. And it doesn't give you insight except in, I guess, the disk space that it takes up, that it might be doing something that's not efficient. So I've got blog posts that will explain more on this, but I promise I'm going to give you more insight into this even today in a blog post because it was a good discussion that I got into this morning, and it ties in really well with what we're talking about here. And I do have an SP Help Index version that explains what's in the tree, and I've even got a version of that I can update. So maybe I'll do a post on that later this week with a newer even version of that. So man, I'm giving myself a ton of work here. So let me round out the slides. I'm actually almost done. But I want to round out the slides and do my last demo on this. But imagine a table that has 8 non-clustered indexes and 10 million rows. I mean, 8 non-clustered indexes is not that out of control. That's pretty reasonable, right? So the question is, how much space is required just for the lookup component that has to go into the non-clustered index if you have a clustering key of 4 bytes, a clustering key of 8 bytes, a clustering key of 16 bytes, blah, 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 blah. And that's what I did. I started to do the math. And these are just for a single table, right? If I have an integer, the lookup space, if I've got, and this was 8 non-clustered indexes and 10 million rows, is only 300 meg, right? But if I've got a composite, like a natural key, it's almost 5 gig or 4.5 gig, right? So that's huge because this is just one table with only 8 non-clustered indexes and only 10 million rows. both of those are fairly low, very, I think, reasonable, like 8 non-clustered indexes is reasonable, and 10 million rows I would say is pretty low. So let's expand it, right? What if I have 100 million rows and 12 non-clustered indexes, which I still don't think is that out of control. But look at those numbers. This is crazy. Using an int only takes me, 4.5 gig or so, but using a composite, nullable 128 character, which is often what happens with natural keys. It takes 6 or 8 columns together to uniquely identify the rows. And we're talking about 150 gig, right? So we're talking about 4.5 gig or 150 gig. And this is for one table, right? One table. And only, let me stress this, only 100 million rows. For those of you that have a billion rows, do the math on that. That's 1.5 terabytes of nonsense if we're talking about a natural key on that monster table, right? That's crazy, right? So my point is it's at least gigabytes, right? You guys are potentially wasting gigabytes. And again, disk space is probably not the biggest problem for you. It's memory. You guys don't have on all of your servers terabytes of memory. And as a result, that's where you're going to really suffer. You're going to suffer on inserts and updates and in logging, right? You're going to suffer in all of your maintenance requirements, and it really does add up. So let me show you a good example. You really need to think about this. My example came originally from the fact internet sales table in AdventureWorks. And I remember looking at the clustered index of the fact table, internet sales, so a sales table, what I would hope is your biggest table in the database, right? I mean, you have a lot of customers, yes, but I hope you have even more sales. I mean, duh, right? Otherwise, maybe you wouldn't be in business that long, right? So your sales table is the largest table that you have. And I looked at it initially and I said, okay, the clustered index is a composite key that consists of the sales order number and the line number. So each sales order might have multiple lines, and in the fact internet sales, each line is essentially a unique row. So I thought, okay, that's a perfectly valid clustered index. And I looked at the non-clustered indexes and I started saying, okay, ship date, currency, customer. I mean, these are all things that we might want to look up based on, a customer key or an order date, although many of those start becoming range-based queries. And I have to admit, narrow non-clustereds are not my favorite for a whole bunch of range-based queries. Another big discussion right here would be, I don't even think this table is very, very well indexed. So I was kind of zoomed in right away when I first saw this table. But then I was horrified to find out that what I thought was a good clustering key was horrible, because the data type for sales order number, is not a number. Right? I looked at the data and every single row was SO and then like 1, 2, 3, 4, 5. SO 1, 2, 3, 4, 6. SO 1, 2, 3, 4, 7. And I remember thinking to myself, oh, well, there must be other types of sales orders, right? Or maybe credit memos, debit requests. So there's got to be something else. And then I looked at all of the sample data, and there wasn't a single row that wasn't SO. So they were trying to make the, sales order number, I don't know, more readable or something to the client. So they put SO in front of it, and that completely wastes space. Now, how much space? Let me show you. Okay, so I'm going to give you guys this script. You can use this really on any version of AdventureWorks. I happen to be using it against AdventureWorks DW 2012. So if you do this against another AdventureWorks, your numbers might not be exactly the same as mine. And you can download AdventureWorks from CodePlex. So I'll go quickly look at my fact internet sales table, and I'll show you my sales order number is that nvarchar 20, which happens to be a max of 40 characters, right? So nvarchar 20 has a length potentially of up to 40, but sales order line number is a tiny int. Okay, so there's our data. And then you can see the indexes down here, right? The other indexes, as I showed you guys, there were things like ship date, currency, and then, of course, the clustered indexes, sales order number, sales order line number. So this is, at the bottom of the screen, exactly what SP Help Index tells you. It just tells you what was explicitly defined in that index. So now I'll do a rebuild just to make sure if there's any fragmentation, it doesn't cause me any extra wasted space. And then I will create a copy of Fact Internet Sales called Fact Internet Sales 2. So let me drop it if it exists. And the way I'm going to create Fact Internet Sales 2 is exactly a copy of Fact Internet Sales. I promise this is every single column of Fact Internet Sales in AdventureWorks DW 2012. So if some of you guys use a different AdventureWorks, they might have a different schema. I can't remember what they changed version to version to version. So you might have to check to make sure that you have every column represented. But of course, I'm going to change the sales order number to actually be an integer, starting at the third character and going 5 characters. There's only 60,000 rows by default in AdventureWorks DW 2012, so it's only a 5-digit number, so you might have to look at that as well. But you can see I just put 60,000 rows into my copy of Fact Internet Sales 2. I'm going to make the sales order number not allow nulls because I'm going to put it into a primary key, and one of the other rules of a primary key is none of the columns that exist in the primary key can allow nulls, so you have to make sure that they don't. So here's my primary key definition, sales order number, sales order line number. I'll create that. And then like I told you, there's 7 non-clusters, so I'll create those. And then we'll just do an SP Help Index. This is my version of SP Help Index. You know what? I was actually working on my new version of SP Help Index just the other day, and I was in the midst of testing it. I didn't even think of that for today. Bad, Kimberly. Demo fail. But I can fix this in just a second by recreating that bad boy and then rewriting this. There we go. Sorry. Okay. So here, and so my version of SP Help Index requires another stored procedure to do something called expose the column. Well, I'm not even going to show you this, but if you scroll way over in my version, I actually show you what goes into the structure of the index, which I'm not even talking about here. So I'm not even really using this part of it, but that's what expose columns in the index does. But here, I just want to prove to you right now that I have the same clustered, right? And let's just keys, right? That's the sales order number, sales order line number. You can see that down here. That's keys are the same. And then currency, customer due date, currency, customer due date, order, product, promotion, ship, order, product, promotion, ship. So I have exactly the same indexes on both my tables. The only difference, right, the only difference between my two tables is the definition of that column. That one column right here, sales order number in the original table is SO, blah, blah, blah. And in my new copy, I've stripped out the SO. And, of course, I've made it an integer because I can use integer here. Now, how does that change the structure? I will look right here, and just looking at the indexes, it's not real obvious here, but the row sizes are different. The index sizes are different. And what that really translates into is disk space. Now, my table only has 60,000 rows, so it's not that exciting. But the original table at 60,000 rows is almost 30 meg, whereas with my table, it's only 18. And the data size is a little different, of course, because I'm using the varchar 20 up here, or the n varchar 20 up here, and an integer here. So the data size is slightly different. But it's not the data, it's the indexes. Look, I'm only just into 7 meg down here, whereas I'm 14 meg here. And I remember the first time I ever demoed this for somebody years ago, and they said to me, that would never happen on a big table. So a long time ago on AdventureWorks DW 2008, I blew up the AdventureWorks table from 60,000 rows to 30 million rows, but I also fixed Fact Internet Sales to be an integer, and then I created a copy of Fact Internet Sales that uses the n bar chart. So I'm just going to, you know what, I'm going to cut to the chase because we're a little bit late on time, and I'm just going to go down here and look at the space used on my 31 million row table, right? we're looking at just under 4 gig in data, just over 4 gig in data. Of course, the data doesn't change much, but we're looking at a massive amount of index space versus the integer-based table. And the more I'm looking at this, you know what? I think I may have goofed around with this one. So hold on, I might have some extra index structures in there that aren't fair. And yes, I do, because it's even worse than it normally is. So you can see here 10 and 8. Yeah, I have 2 extra indexes that I shouldn't have, but obviously this has happened to me before. And I have it right there. So I'll do that. This database, I don't backup restore every day because it's kind of a monster. But there you go. So we're looking at 8 gig versus 3 gig, right? So 3 gig for my integer-based table and 8 gig for my bar chart. Isn't that crazy? This is huge. And this table only has 30 million rows and only 7 non-clustered indexes. So my point, which I've gone a little bit over here, is it does matter. It does make a difference. I want you to think about that physical design and its implication. If you do some prototyping and try a couple of different options, you might be surprised to find that you have a much more scalable structure just by tweaking a few of the data types. And it matters most in the monsters, right? The 6 or 8 tables that are those big tables that are going to end up having hundreds of millions, if not billions of rows. Okay, so I have lots of questions I want to talk to here. You know, for a clustered index, if we have a table where a natural key is a varchar 50, should we use the natural key as the clustered instead of a generated ID to avoid the key lookup, since most of our queries are on the natural key? That's a great question. I know you say that most of your queries are on the natural key, but the keyword most makes me at least ask, are there any other lookups? Because as soon as you start having 1 or 2 or 3 non-clustereds, then even if most of the queries are using that key lookup, you still might make those other non-clustereds so inefficient that it would be better to have created something like a surrogate key and cluster on it. It's tough though. It's really, I'd have to do some prototyping, some testing with the combination that you were considering. Oh, somebody here says, speaking of the range, don't be afraid to start with negative numbers. That's a great point, and it's also a great way to fix the problem with an integer, for example, running out at 2 billion, is that you could go to negative numbers. So I mean, that is something that you can do, and it's certainly a lot less of a fix to deal with in your code and so forth, right? Let's see. I'm trying to look at some of these. I've got some thank yous. You're welcome, you guys. I know I'm starting to lose a couple of folks because I ran a little bit long. Don't forget to get the Pluralsight code if you guys want to see a longer version or have some colleagues look at some of the stuff that I did today, including that demo that I did. Somebody else said the best way to answer the presentation is, as always, it depends. And that is a great point. It's true. I mean, there's no one single right answer for what should my clustering key be. I mean, I'm with you. I totally agree. It does depend. But I at least wanted to spend today talking about some of the things on which it does depend so that you can make a better decision. So let me see what else I have here. I've got some funny comments as well. Yeah, some folks saying that they didn't know that the clustering key would have, or non-clustered indexes would have that clustering key column added. And yes, but it doesn't put the column in there twice if the non-clustered index has those columns like I showed you guys. So you guys have that one. So all of the columns of the clustered are part of the non-clustered, and the unique identifier is added as well? Yes. So that uniqueifier, if the clustering key column is non-unique, does get added to the non-clustered index. you know, and here's another one. So if you have a multi-column clustering key, are you suggesting it's better to use a sequence identity and make a unique constraint for the columns that would be otherwise would have been that composite key? In a lot of cases, yes. I mean, in the case that I showed you where we had a sales order number and a line number, if both of those had been a number and both of those had been defined efficiently, then the composite key is fine. So I want to stress that I'm not against good, efficient composite keys that are narrow. And there are many cases where I would have a composite key over just arbitrarily adding another sequencing type of ID. So I wouldn't just do that. But in the case of like a products table, if it takes 7 or 8 columns to uniquely identify a product, then yes, I'm a much bigger fan of also having a product number and having that product number very likely be the primary key, very likely be clustered, and then having a non-clustered unique index or constraint that handles the uniqueness of the combination of those columns that is the natural key. So I think I've got quite a few things. There is a comment that Oracle has hash indexes for that. SQL Server can do some interesting things internally with what we call bitmap indexing. It's not a direct comparison to Oracle's hash indexing. And there are ways to do even more performance tuning on certain tables and structures, a little bit beyond the scope of today, but it's not a direct comparison. I just wanted to stress that. I think I've got, right here, what's this one? If you work on 2014 or less and your company has no plans to move anytime soon, do yourself a favor and find another job. That's a funny one. That's not my quote, but I do have to admit, if you're on a really old version of SQL Server, it's out of support for Microsoft. So you could really find yourself in a lot of trouble. So you really do want to be on at least 2012 or higher. And in terms of your upgrade path, to me, there is no other version to consider other than 2016 from a testing perspective. So I think I've got most of these. Some of them are a little bit just beyond the scope. Wait, I'm trying to see if I understand this one. Will you be able to speak briefly about the transaction log impact when using index, reorg, or rebuild? It's a little bit out of scope. A rebuild is a fully logged single transaction, whereas a reorg is a reorg on the log can actually require even more, but it usually requires far less. And it's also not a single transaction, which is also what can make it much more efficient. But I would argue that if you really want to understand reorgs and rebuilds with regard to transaction logging, Paul's Pluralsight course on fragmentation goes into great depth on that one. So that one you can definitely get more info on. Whoa, okay, I just scrolled down to the window. There's a bunch of other comments. Lots of thank yous, so you're welcome, you guys. Yeah, this is a great question. Is there going to be a chance of a Pluralsight class on partitioning? I really hope so. It's on my list. I've got a few other courses that are much closer than that one. I have a class on indexing and a class on statistics that I'm working on next. And those are much closer. I just have to get everything wrapped up and get those online. Let's see. I love the assassination of goods. Yes, you're welcome. No, this is great. I think in terms of time, I'm going to end it here. I think I've got most of these. I know there's still a few more. I could probably talk for another 3 hours, but I hope you guys enjoyed today's presentation. I will bundle up all these resources next so that you guys will have the demo script and the slides and the reminder to send email to Paul to get a Pluralsight code. And outside of that, I really appreciate you guys sticking around. In fact, there's still so many of you, almost 2/3 of you stuck around to the very end. So thank you very much, and I hope you guys enjoyed this, and have a great day.
Thank you very much, Kim.
Thanks, you guys. I'll bundle everything up and send this to you in a second so that you've got this.
All right. Thank you, everybody. Thank you again, Kim. We'll see you next month.